Good morning. It's early, and in fact, we have competition. My colleague in electrical engineering, Eric Popp, is doing Thermoelectrics 101, a short course in parallel. This is, in fact, a research project with Jens Norskov in chemical engineering and Piero Pianetta in SLAC and EE. The target, however, is not thermoelectrics with our low work functions, it's thermionics. So let's dive in, and I'm going to give you some motivation and background because, in fact, thermoelectrics are a well-known technology advancing through the efforts of GCEP funding, making a major impact. What about thermionics? It's a century-old technology. There is it's basically a diode. The anode or collector's work function is critical in the efficiency of this device, and that would be a target. There's also the emitter or cathode, and that work function is somewhat less critical, but some of this work could be dual use for either electrode. We've spent a lot of time working on alkali earths and computational modeling. Also some breakthroughs in modeling the emission current from first principles, which is a first in addition to the work function. Sometimes you have a material with a superb work function, but an incredibly lousy emission current density. So that the ability to compute that is important. We're working on some alternative anode approaches, and I'd like to wrap up with future prospects for thermionic energy. So here is an expanded view of this very simple idea of heating typically a metal, though I'll indicate some breakthroughs and alternatives to metals for the cathode, and simply collecting those emitted electrodes at a material at a different temperature, cooler temperature, and different work function. You have something that looks like a photovoltaic cell in that it gives low voltage and high current. If we do our energy band diagram, we see that our output voltage, ideally with no losses, would be the difference between the emitter and collector work functions. Therefore, the collector or anode work function needs to be minimized. The Richardson-Dushman law developed in the previous century, that constant A is important as well on the cathode. There are issues in radiative heat transfer I'll go into in a minute because of the large temperature difference. There's also losses through the leads, through the interconnects that would hurt your efficiency. So through the 20th century, there was a tremendous development in thermionic converters. The basic concept, Schlichter in his PhD thesis at Tübingen almost 100 years ago, introduced in an appendix the concept of the thermionic converter. Soviet researchers in 1941, in fact, the first work is in World War I and the second in World War II, under interesting conditions, no doubt, but they did a lab demonstration, and after the war, tremendous efforts in the US and Soviet Union for space power using nuclear pile sources, but efficiencies were achieved of 5 to 10%. Ultimately, there was a conference in 1968 where the communities decided they were efficient enough at 20% for their space applications. Just to show you that these existed, this is a Topaz 2 built by the Soviet Union, flown 27 years ago on a naval reconnaissance satellite, and it's a 6 kilowatt nuclear reactor wrapped with a thermionic converter. Some materials issues being wrapped around a nuclear pile. And in fact, after the Cold War, we leased a dozen of these and tested them. This is a photograph of a US plane with a Soviet converter. So in any case, in the 21st century, we do have very high temperature sources of heat. This is a concentrated solar plant in Spain. And we have, in fact, the Ivanpah CSP plant that's come online in the Mojave Desert this year in March. And so perhaps this needs to be revisited. after the Cold War, this is a capsulated perspective, the technology developed was tungsten with adsorbed cesium to lower the work function. The electrode gaps were held at 100 microns, a tenth of a millimeter over large areas. I'm sure there were heroes of Soviet labor for the machinists on these projects. This was done in an era where cost was not an issue. Observing US ships on the dark side of the earth was an issue for the Soviet Union and also for the US. Lots of workarounds. So in any event, there was a study, Thermionics Covatus, that looked at this about 13 years ago, and I'll reference that in a minute. We've had a wonderful collaboration under GCEP funding, and in fact, other investigators that would be involved. This would be a paper with Nick Malosh and my former postdoc, Igor Bargatin. Jay Lee is a grad student, wrapped up his PhD last year, where we looked at the optimal electrode gaps. In fact, the 100 micron gap, you would have space charge issues that they battled. We can make gaps using MEMS technology well below a micron. Is that desirable? Turns out that you have these near-field heat transfer effects and you get thermal shorting, so there should be an optimum. And Murphy must have been asleep because the gap of 1 to 10 microns is something that is like falling off a log for people making gyroscopes and accelerometers, which I spent a good part of my early career, silicon gyroscopes and accelerometers using MEMS technology. So in fact, that's great. We can make it, possibly in technology that would drop the cost orders of magnitude using wafer scale fabrication. However, I referenced that Thermionics Covatus report. In that report, there was late 90s work on a wafer-bonded thermionic concept at Sandia National Labs. The criticism of the panel was that the heat, thermal isolation would be a showstopper. You have differences in temperature of 500 Kelvin or more, gaps of a micron. You have tremendous gradients. How on earth can you possibly have that kind of gradient? You'll have thermal losses will make this inefficient. Well, in fact, I've been on these panels. It's interesting to make this kind of quote because you can always cover yourself by saying you were sort of provoking people. You know, you knew that this wasn't the case, but why not, jab the community? In fact, thermal isolation microplatforms have been well known since the 80s and 90s. Bolometers are a very hot commercial topic for infrared cameras for automobiles. They're made using these suspended platforms, and the detection temperatures are millikelvin. You're thermally isolated from the substrate. And in fact, these are fabricated using the kind of micromachining technologies that would be the subject of basic grad courses at Stanford. In fact, we've applied that technology to make a suspended structure out of silicon carbide with no no tungsten, no work function coating, just as an existence proof. And in fact, we ran it as a converter using the silicon substrate as the anode. What would the converter look like on the Ivanpah Tower? Massive arrays of pixels, possibly individually addressable. EEs like that idea. We can do some interesting things with access to that at that level. So actually, optical heating of this, we don't have any problem going incandescent and keeping the substrate quite cool. And so thermal isolation in a vacuum is a non-issue. In fact, vacuum is also a non-issue. I think there may be some interesting practical challenges for long-term reliability, but in your pocket you have a gyroscope chip, if you have an iPhone, that would be made using wafer-bonded seals using basically a variant of MEMS technology. So the ability to fabricate this is not a problem in principle from my perspective. Unfortunately, the materials, silicon carbide is not a candidate. It may be a structural material. If you look at the efficiency of the thermionic converter with the cathode temperature on the x-axis and efficiency, the These are ideal efficiencies without losses. This is the collector or anode work function. Going to very low work functions is important. Nanocrystalline diamond has been under 1 electron volt. In fact, we have, we'll report things that are on the order of 1 eV, and these efficiencies are, in fact, in context, we may be a topping cycle on that Ivanpah plant. We may not replace the conventional heat engine. Our reject temperature could be quite high. So in any case, how do we find these materials? And now we get to this particular critically important GCEP grant because, in fact, people have made, there's a whole industry with electron sources, SEMs, electron beam lithography, instruments of all kinds, and these are often made with a tungsten base metal, typically not crystalline, coated with a mixed oxide, alkali earths, barium, strontium, calcium, sort of mixed up in a mortar and pestle kind of fashion in some cases, and deposited in interesting ways with migration into the grain boundaries, and ultimately a very complex process leading to electron emission and low effective work function. So what this project proposed to do is look at this from a systematic point of view. And in fact, we have the question of where to start. The most favorable, most stable configurations have, in fact, the x equals 4, and so we focused on those. I will go into a lot of simulation in the next slides. It's just recently been in the literature with several papers with my student Sharon Chow as the lead author. But in context, the fabrication technology where you would engineer the composition of these would be, from my perspective, done using atomic layer deposition, which is a very powerful tool. We are currently depositing strontium oxide on tungsten for example, but there's work in the literature where you would nano-laminate these materials between strontium and barium and calcium, and then do post-processing to center and dial in that composition very, very tightly. So focusing on this set, we still have a lot of simulation to do because we have our basic alkali earth is calcium, strontium, or barium, and we can dope that. In the literature, there's a lot of work on adding things, lithium and other metals. So what is showing here is a virtual atom that could be a blended composition of the pseudopotentials of these 3 atoms as a shortcut. And obviously, the unit cell that's being simulated is important to minimize that. And it was very important to have access to the SunCat cluster up at SLAC that Jens Norskopf would be in charge of. This is a very serious, big iron kind of computer. So if we basically, we have this unit cell, what we would like to do is identify dopants that would dopants and compositions that would drive us in 2 directions. We want very large negative formation energies for stability. There are things like dispenser cathodes that spew out some of these materials. We want a rock-solid, stable material. Ideally, for those that are in the electron emission business, we would not want cesium in this. That's a difficult material to deal with, and can we do it with simply our mixed oxides? So we're driving in a direction of low work function and stable formation energy. And if you look at the various dopants we can add, they have effects that would often be useful. So we would be focusing on ones like scandium and lithium that would make this material more interesting as an emitter. So we're faced with a large triangle of potential compositions. and how to deal with these simulations. Well, Sharon Chow, my first student who has not gone into a bunny suit into the nanofab in my entire career, though an EE, looked at basically doing it brute force with the actual atoms and expanding the unit cell. And this leads to around a week runtime. The virtual crystal approximation shrinks the cell, and you get down to hours. And in fact, the differences in some test cases are rather minimal. So there's an incentive to just get started. And of course, the blending of these pseudopotentials is very important in order to get both computational feasibility and benchmarking against experiment to get accuracy. So Sharon's process would be to get the atomic orbitals, generate smooth pseudopotentials from these orbitals, check the answer, reformulate, and repeat. Fortunately, you can write scripts to do this, assuming SunCat isn't crashed by your activities. And she did have her hand slapped for excessive consumption of SLAC's computing resources. Nevertheless, it was a very, very interesting result. What are we showing? We have the pure mixed oxides with all compositions, with work functions and formation energies, adding scandium and lithium doping. And this is work functions and stabilities, 570 total combinations. So what this does is short circuit a massive amount of experimentation. And at the Three Beams conference, which is where the electron beam people hang out, this is of great interest. They have been mining this for a number of years using technologies that are not as controlled as ALD. And so, in fact, if you look at the pure films, it looks like you can benefit going to, and so I'm mapping pure barium oxide and a work function of around 1.5. And in fact, if you look at what calcium is doing, calcium, the addition of calcium is in fact driving the work function higher. However, it's making the formation energy lower, so it's a kind of counter effect. And so you may be able to see adding a pinch of calcium to get that surface stability while maintaining the low work function. Now, there is an experimental ratio here from a paper about 13 years ago, and so we would be benchmarking in the very limited experimental data. A lot of this is proprietary, actually, in the industry. So if we add lithium, we can get work functions of 1.2 eV and as stable as the pure material. I'm going to click through this quickly. And so it looks like we have something that could be a potential candidate for a cathode material or an anode material. The understanding of this, I'm going to look at, you can read the details in the paper. Work function is a function of the effective offset of the, this synthetic atom from the oxygen at the surface. And in fact, that could be a physical insight in how you can control the work function. So in any case, where are we? Okay, in this. This was shown earlier. If we indicate our lowest work function at 1.15, we are getting efficiencies that are in the range of 30% ideally. Again, we may not be rejecting the heat at 300 Kelvin. It may be a topping cycle, but compared to their initial work functions and without cesium, I think this is a very important breakthrough. We would be gearing up to do this experimentally. Along the way, there were a lot of discussions on the inability to simulate the current density using density functional theory. Johannes Voss at SLAC and Frank Abel Peterson developed a way of extending the supercell into the vacuum and adding a decoupling region to the lead, to the interconnect, and essentially first principle simulating the current and benchmarking that against experiment. So now we have the whole basic function of that high temperature material, work function and Richardson-Dushman coefficient for the first time on the, our ability is to simulate that to compute before we do the fabrication. Lastly, another paper with Johannes would look at the lanthanum hexaboride, which is a standard cathode material with a layer of barium hexaboride. You're able to lower the work function by 400 millivolts without any dipole barrier. So one challenge in talking over with, can we go synthesize this? That has proven to be challenging to do what would amount to be an epitaxy of a monolayer is currently beyond our technology. But this would point in a new direction for getting materials that are fundamentally higher performance, maybe lowering the working temperatures substantially. Finally, we've worked on other ways to lower work functions. This is, as an electrical engineer, we think, well, we must be able to mess around with this using some gate or something to get what we want. Unfortunately, in a three-dimensional material, we of course can do what we've been doing, lowering the vacuum level using surface coatings. Maybe we can raise the Fermi level. It doesn't work in 3D materials, but it does work in 2D materials. In Philip Kim's group at Columbia, this was shown for transistors. So my student Hong Yuan is working on doing this for Thermionics, where we would have a control through the substrate to do what we call electrostatic doping of the graphene, raising the Fermi level and lowering the work function. So we've been working on this with tremendous experimental challenges to get high-quality graphene. And over the summer, Hong Yuan, using a Kelvin probe, has been able to show a very substantial shift in work function. And at SLAC, we're not getting quite the same shift, but still a much larger shift than has been shown in the literature. We have a larger spot size, and the graphene isn't perfect. So finally, we are building up a test station for micro-thermionic converters. This is the SolidWorks drawing. Hong Yuan's a physics student, but has come up to speed in vacuum technology. All told, in our multiple groups, we have 5 chambers for testing these. This is a new one. And so wrapping up, what are the prospects for wafer scale thermionic energy converters? Say wafer scale, these chip-based technology, MEMS technology. Well, I think they're very simple devices that have some very challenging materials issues, high temperatures. There would be a large push in MEMS to go embrace silicon carbide. My colleague Debbie Sineski in Aero and Astro would be working on high temperature sensors for combustion and gas turbines. That technology very much overlaps with what we would need in thermionics. So I don't think the technology is an issue. I think the GCEP project has made a huge whack at the materials challenges and kicked off something very, I think, very exciting. Nick Malosh isn't here today because he's in Houston at a NASA conference on thermionic energy conversion. That would be where I would be if I wasn't giving this talk as well, because I think what has been happening in GCEP and overlapping projects is very exciting. So lastly, the photon-enhanced thermionic energy converter, which was Nick and his student Jared Schwede's invention a few years ago, would use a semiconducting photocathode. All of this work on the anode is valuable. For the Pete converter as well as the straight thermionic converter, as we call it. So that is a exciting thing. So I'd like to wrap up. GCEP has played a critical role in enabling this simulation project. Frank Abel Peterson, a senior author, the resources of Jens Group in Sun CAD have been critical. And my group on the experimental side, Sharon is now at First Fuel, a energy efficiency company. She finished her PhD. Igor is a professor. Jay, a CEO of a startup. And Nick and ZX's group would be part. We have a large overall Thermionics meeting and separate meetings. This has been a very exciting research project, and GCEP has been absolutely critical to kicking this off. Thank you.
So. Questions?
Yes.
Wait for the microphone.
Okay.
How big a role does radiation heat loss play between the emitter and the collector?
It's certainly always there, but it is a tremendously strong function of the gap. There's sort of classical radiative heat loss, and then there are these near-field effects that have been modeled in recent years. And we are comfortable in this 1 to 10 micron range, but going closer than a micron, and it actually will short out your converter. You won't be able, you'll have such radiative losses that you don't have any efficiency. But it's not a complete showstopper by any means.
If you treat it as a topping cycle, is it the same efficiency just with a smaller amount of the energy, or do you actually increase the efficiency for like basically that portion of the energy that you're going after?
It would be an interesting complex optimization problem. And we went up, Nick and I, to BrightSource, the Ivanpah designers, and they would be very interested on when this is coming online. There's tremendous efforts on the primary heat engine. If you have from left field something out of almost the semiconductor industry that you could put on that tower as a topping cycle, maybe it takes some pressure off them. But the numbers would be really encouraging if you give it even a 15% boost. That really matters. So it's a work in progress. I might mention that Jared has won something interesting from the Department of Energy, the M37 program at Lawrence Berkeley National Lab for incubating ideas that need more time but have tremendous commercial progress. So promise, rather, and he proposed thermionic converters and won. And so he's looking forward to wrapping up his PhD and heading up there, possibly with Dan Riley tagging along. He's in Nick's group. So I think it's something that I have spent a lot of time talking on the overall picture, because perhaps that might be not as familiar as other energy conversion. With the centenary coming up next year, I think it's high time that we really apply some push in this as a complement to other energy conversion technologies. So. Oh, okay.
So the graphene idea is really interesting. Using can you hear me?
We have the chairs. Oh,
So the graphene idea is pretty interesting, using the gating to change the work function. How much can you do at the end? Because of gate coupling, eventually will have a limit. Yeah.
Well, it would be with this, and I forgot to mention that it had no dipoles or anything, so the work function is way too high in graphene to vacuum. We need to put something on it to drop the work function, then yank it around electrostatically. We think we can get under 1 eV. And the voltages needed were not particularly high. And there's no current, of course, and the anode is relatively cool, so you don't have to envision this operating at outrageously high temperatures. Hong Yuan is very much interested in pushing that.
Okay. Let's thank Roger again.